You know when Netflix just knows the next show you're going to binge? Or how your phone can pick out every single picture of your dog from thousands of photos? That's not magic. It's actually all about teaching a machine how to learn. So today, we're going to pull back the curtain on artificial intelligence by enrolling our very own virtual machine in its first day of school.
So that's the big question, isn't it? How do you actually teach a machine to think? To figure it out, we're going to follow our new digital student as it attends Machine University. We'll be there for its first lesson, we'll watch it study, and we'll even be there for its final exam to see how it learns to make sense of our world. All right, so here's our machine's class schedule for the day. First, we'll cover the absolute basics of what it means to teach a machine. Then, it's going to tackle its first subject, learning with a handy answer key. After that, we're taking the training wheels off and making it find patterns all on its own. Next up, a little group study. And finally, the final exam. We'll grade our machine and see how it did. Let's get into it.
Okay, first period is in session, Machine Learning 101. And the most important lesson here is this. Instead of a programmer sitting down and writing a rule for every single possible situation, we build algorithms that let the machine figure out the rules for itself, just by looking at tons and tons of data. Think about it this way. For decades, programming was like writing a very specific recipe. Add 2 cups of flour, then 1 cup of sugar, then mix for 3 minutes. The computer just follows instructions. But with machine learning, it's totally different. We show the computer 1,000 pictures of a perfect cake and say, you figure out the recipe. It learns to see the patterns and deduce the rules on its own. It's a real game changer. So let's move on to our machine's first big subject. It's called supervised learning. And honestly, the best way to think about this is like we're giving our machine a massive stack of flashcards. On the front of each card is a question, and on the back is the correct answer. The machine just studies thousands or even millions of these already solved examples until it starts to get it. And in this particular class, our machine is going to tackle 2 main topics. First up is regression. This is all about learning to predict a number, like what's the price of a house going to be, or what's the temperature tomorrow. The second subject is classification, which is more about sorting things into groups, like deciding if an email is spam or not spam. Let's zoom in on regression for a sec. A really classic way to do this is with something called linear regression. The machine's job is to look at a bunch of data points on a graph and draw one single straight line that best cuts through them. The best line is just the one that gets as close as possible to all the dots. We call this minimizing the error. And once it has that line, it can predict where the next dot is going to show up. Now, with classification, the goal is a little different. Instead of predicting a value, the machine's trying to learn how to draw a line in the sand, a decision boundary that separates different groups of things. Think cats and dogs. Everything on one side of the line is a cat, and everything on the other is a dog. The whole challenge is just figuring out exactly where to draw that line. And one of the coolest ways to find that line is with what's called a support vector machine, or SVM. See, an SVM isn't looking for just any line that separates the groups. It's on a mission to find the line that creates the widest possible street between the 2 groups of data. The bigger that gap, or margin, the more confident the machine can be about its decisions later on. It's a really smart approach. All right, so our machine has totally mastered learning with an answer key. It's time for its next class, Unsupervised Learning. And for this one, we're going to throw it a curveball. We're taking the answer key away. We just give the machine a giant, messy pile of data with no labels and say, okay, find something interesting in there. The main assignment in this class is something called clustering. The whole idea is for the machine to look at all this chaotic data and find its own natural groups. Imagine giving it a database of all your customers. Without any help, it might start to find clusters like loyal high spenders, weekend window shoppers, and bargain hunters, categories you never even knew existed. And one of the most common ways a machine does this is with an algorithm called k-means. The k in the name is just you telling the machine how many clusters to look for. So if you say k equals 3, it'll look for 3 groups. The means part refers to the center point of each of those clusters, which the algorithm tries to place in the perfect spot. The way it works is actually pretty cool. It's like a little dance. First, the machine just randomly guesses where the centers of the clusters are. Then it looks at every single data point and assigns it to the closest center. After that, it recalculates the center of those new groups, and it just does that over and over and over again, assign, update, until the centers stop moving around. Now, k-means has a close cousin called k-medoids, and the big difference is how they define the center of a cluster. K-means just calculates the mathematical average, but that can get thrown off by weird outliers. K-medoids is a bit tougher. It insists that the center of the cluster has to be an actual, real data point from the group. This makes it way more resilient when the data's a little messy.
So our machine can learn with help, and it can learn on its own. Now it's time for some advanced group study. This is where we get into what are called ensemble methods. And the philosophy here is super simple. Teamwork makes the dream work. By combining the predictions from a whole team of models, you almost always get a better, more accurate results than any single one could achieve alone.
There are two main strategies for this kind of teamwork. The first is called bagging. This is kind of like creating a bunch of student models and giving each one a slightly different study guide. Then you just average all of their answers. The other strategy is boosting. This is more like a relay race. The first model makes its best guess, then the second model comes in and focuses specifically on fixing the first one's mistakes. Then the third one corrects the second, and so on. Each one learns from the last.
Okay, the bell has rung, class is over. Our machine has gone through all its lessons. But did it actually learn anything? How do we know if it's ready for the real world? Well, it's time for the final exam.
Let's see how our student performed on the big test. Now, the first page of its report card is called the confusion matrix. I know, it looks a little intimidating, but it's actually really simple. It just shows us where the model got things right and where it got, well, confused. A true positive is a correct yes. A true negative is a correct no. But a false positive is a false alarm, and a false negative is when it missed something completely. So from that little table, we can calculate its grades. The most basic one is accuracy. It's super straightforward. It's just the number of times the model was right divided by the total number of predictions. This is like its overall final score. What percentage did it get correct? But sometimes just knowing the overall score isn't enough. We need a more specific grade, like precision. Precision asks a really important question. When the model said yes, how often was it actually right? This is absolutely critical in places like medical diagnoses, right? You don't want a model that has a bunch of false alarms. And on the flip side, you have recall. This asks a different question. Of all the yes cases that were actually out there, how many of them did our model manage to find? High recall is essential when missing something would be a disaster. Think about airport security or trying to detect credit card fraud. You want to catch everything you possibly can. So the whole point of this entire final exam is to find the perfect balance. We need to avoid underfitting, which is like a student who didn't study at all. The model's just too simple to understand what's going on. But we also have to avoid overfitting, which is like the student who just memorized the answers. The model looks perfect on the practice test, but the second it sees a new question, it completely falls apart. Finding that sweet spot right in the middle, that's the whole game. And there you have it. That was our machine's first day of school. We've seen it learn with help, discover patterns by itself, and even work in a team. The whole time, we've been focused on what we can teach the machines. But that really leaves us with one last big question to think about. What will they eventually teach us?